Hi, and welcome back to the Implementing and Administering Cisco Solutions, the CCNA 200 video series course by EC Council. My name is Glenn Singh. This is part 2 of the video for IPv4 addressing and subnetting. In this video, we're going to focus on what exactly is subnetting, and we're going to take a look at a practical example of working out a subnet for a small network. So let's dive in. So why do we subnet? What is the benefit of subnetting? To put simply, subnetting has two primary benefits. The first benefit is to efficiently distribute IP addresses with least wastage. This benefit is very essential, especially for the IPv4 public and private address space. Since there are only approximately 4 billion public IPv4 addresses, Internet service providers and other regional internet registries needed a way to be able to distribute IP addresses to end device and devices on the internet without wasting any amount of addresses. So the technique of subnetting comes in, which simply allows us to efficiently distribute IP addresses on a network without wasting too much. The second benefit, or the second purpose of why we subnet, it is to create more networks with smaller broadcast domains. So now let's take a look at a small network that we need to create a subnet for. Looking at this topology, it's a hub and spoke topology where we have the HQ office that is operating as the actual hub. As we can see in this network, we have 3 WAN links. Furthermore, how many LANs do we have as in local area network? Well, there's a LAN for HQ, which consists of 28 hosts. There's a LAN for branch A, which consists of 26 hosts. There's a LAN for branch B, which consists of 25 hosts. And there's a LAN for branch C, which consists of 15 hosts. So therefore, we have a total of 4 LANs. Now, the total number of networks, well, 3 plus 4 is equal to 7 networks in total. What if the senior network architect says, hey, we want to keep our IP addressing very consistent, and we also want to ensure that whatever network blocks that we assign to any of our branches, including our WAN links, there's very least wastage. So how can we actually design a subnet scheme for this network? Some persons might say, let's assign the 192.168.1.0/24 network for HQ. And for branch B, we can assign the 192.168.2.0/24 network for branch A. Branch B could be the 192.168.3.0/24. And branch C could be the 192.168.4.0/24. Now, as these addresses will work, there's a very big problem. That problem is each of these networks only require, let's say, less than 30 hosts. So therefore, there will be a lot of wastage of addresses from any of these network IDs that you probably would choose. So let's take a look at different steps that we need to go through to simply ensure that we choose the most appropriate IP address block or the actual IP address class. Then we'll begin to subnet it, as in break them down. We'll create the ranges, and then we'll take a look at VLSM. So the very first step, it is to simply determine an appropriate address class for our network. The second step is to calculate each subnet or each subnetwork. The third step is to actually assign each subnet and their corresponding ranges to the actual networks. And then we'll take a look at step 4, which is performing something known as variable length subnet mask, VLSM. VLSM, to put simply, is subnetting a subnet. A very big challenge is simply determining which address class we should start with. Should we go to a class A, Class B, or a Class C? Well, to help you determine this, we can take a look at the subnet mask here. Now, the thing about the subnet mask, it helps us determine the network portion of the address and the host portion of the address. Well, in my personal experience, the subnet mask actually help me determine the number of total IP addresses in either Class A, Class B, or a Class C subnet mask. So to put simply, where the ones are located in subnet mask, that simply indicates a network portion of the actual IP address. The zeros indicates a host portion of the IP address. So for example, a Class A subnet contains 8 bits, or the first entire octet represents the network portion of the address, while the other 3 octets, the second, third, and fourth octet, represents a host portion, which is interchangeable. Now, what we can do is simply use a very simple formula. The formula to calculate total IP addresses in any network or in any subnet is 2 to the power h, where h is the number of host bits. So what I did is I actually did the calculation here already. So with a Class A, it has 24 zeros, because these zeros here represents the host portion. So 2 to the power 24 will get 16 million plus total addresses. So therefore, let's say we choose a Class A network, like let's say 10.0.0.0/8, we'll still be wasting 8 million addresses. Sorry, we'll still be wasting 16 million addresses, because we only need 28 for our largest network. If you recall from the diagram, our largest network requires 28 hosts. What if we choose a Class B? Let's say we choose 172.16.0.0/16. Well, substituting the number of zeros for a Class B subnet mask, which means that we have 8 plus 8, which is equal to 16 host bits. 2 to the power 16, we'll get 65,536 total IPs. We'll still be wasting a lot of IPs. But let's take a look at the Class C. The Class C subnet mask only has the last 8 bits for the host portion. So let's say we use an address like 192.168.0.0/24. Well, since we convert this last octet, which is this one here, to binary, we have 8 zeros. So 2 to the power 8 will get 256. Now, our largest network in our diagram requires 28 host IPs. So the key thing is that you want to choose a network ID, or you want to choose an actual address class that can fit your largest network within your company. In our diagram, our largest network is 28 hosts. There's no network larger than that in our diagram. However, our smallest network we have that can fit 28 hosts is Class C. We cannot go anything beyond on Class C. So now let's assume that we are going to use this network here, 192.168.0.0/24. So now that we choose an appropriate address class, we actually complete step 1. So now let's move on to step 2. In step 2, what we did is we took any address within a Class C private network or a Class C private IPv4 network, which is 192.168.0.0/24. Remember, the /24 is a network prefix. So we convert the actual IP address into binary. We convert the subnet mask into binary as well. Remember, the ones in the subnet mask represent a network portion, which we will not touch. And the zeros represents a host portion of the address. So if we use, let's say, our formula, because what we need is 3 formulas. Number of subnets, which is 2 to the power n. Then there's total IPs, 2 to the power h. And then there's a third formula, which is 2 to the power h minus 2. this third formula will give us usable IPs. So let's take a look at the total number of IPs that are available in this network here. We have 8 bits that represents the host portion. So therefore 2 to the power 8 is equal to 256 total IPs. The thing about IPv4 is that we cannot use 2 specific addresses. We cannot use the network ID IP address, and we cannot use the broadcast IP address. So therefore we need to minus these two. So once we minus those two, we actually have the usable addresses. Hence our second formula here. Well, the third one that is. So this is 2 to the power 8 minus 2, which is equal to 254 usable addresses. Now we have a little situation. How can we take this one network ID, which is 192.168.0.0/24, and create a total of 8 networks? Remember, we have 3 WAN networks plus 4 LAN networks, which will give us a total of 7 networks. So we need to break this down as in subnet 192.168.0.0 to create 7 networks, and our largest network requires 28 hosts. So how can we attempt to actually subnet this network here, create our 7 networks, where each of the 7 networks can successfully fit our largest network of 28 hosts? What we can do is simply draw a line right here. Where the one stop in the subnet mask, we are drawing our line. Everything to the left hand side represents the network portion. We are not going to touch the network portion. Everything on the right side of this line represents the host portion. In subnetting, we can borrow host bits starting from this line moving to the right. So let's take a look at if we were to borrow one host bit. So let's draw a little line right here to represent that one host bit. So if we borrow one host bit, our formula is 2 to the power 1 for total number of subnets, which is equal to. So we'll get 2 subnets here. But remember, we need 8. Actually, we need 7. So this is too little. What if we borrow another bit? So this will be 2 to the power 2, which is equal 4. But remember, we need 7. So let us borrow another one. So now we borrow 3 bits on the host portion of the actual address. So therefore, we'll get 2 2s 4, 4 2s 8. We'll end up with 8 networks. But we need 7. So what should we do? Well, if we borrow 1 bit less, we will short of a lot of networks. So it's better we get the exact number of networks, or we go 1 bit higher and the extra network will be used for future reservation. So we have satisfied this so far that we will be taking 3 host bits that will represent our new network bits. But that being said, how many host bits do we have remaining? Well, what we can do is draw another line right here. So now we actually remain with 5 host bits here. So if we substitute in our formula to get total IPs, remember the formula for total IPs is 2 to the power h. So therefore 2 to the power 5 is equal to 32. But remember, we cannot use 2 bits. Well, we cannot use 2 addresses, which is the network ID and the broadcast IP address. So therefore, our new formula to calculate usable IPs is 2 to the power h minus 2. And we are going to say 2 to the power 5 minus 2, which is equal to 30. So what does this mean now? Well, if we use this calculation we have here now, as it is, we'll end up with 8 networks, and each of our 8 networks will have a total of 30 usable IP addresses. So which means that we are fitting the number of networks we need, and since our largest network is 28 hosts, guess what? We can take any of our 8 networks and fit our largest network. Once we can fit our largest network, we can fit all the smaller networks. So this actually works out well. Now what does this mean for us? Well, this means that we actually need to change the subnet mask. So originally the subnet mask is a /24. But since we are borrowing 3 bits, we have to convert these bits here into ones. So we'll be moving from a /24 to a /25, 26, 27. So if I clear up this board a little bit here and actually write out our new information, it will look like this. So remember, we are changing these 3 bits into ones because we choose to use these bits. But we are changing the bits in the subnet mask first. Therefore, this is our new subnet mask. And if we convert it to binary, we'll get this new result. To put simply, this bit is 128 plus 64 plus 32, which is equal to 224. Furthermore, to set our calculation here, we can have 2 to the power, and remember we are using 3 bits now, which is 2 to the 4, 4 to the 8 networks or 8 subnets. And if we use these 3 bits for our network, then the remaining 5 bits will be for host. So let us work out our calculation here once more, which will be 2 to the power 5, which is equal 32, and we need to calculate usable IPs. So we have 2 to the power 5 minus 2, which is equal to be 30. So our formula is actually perfect now. Now let's take a look at actually creating the different possibilities in step 3. So now we already have our subnet mask, and this new subnet mask will now be used for the 8 new networks that we are about to create. So keep in mind that this /24 no longer exists. This new subnet mask, which is a /27, will be used for these 8 networks that we are creating. Now in the third step is where we actually have to create the subnets. So what we'll be doing is, since that this portion here between these 2 lines is the bits that we will be changing in the actual network ID here. So we have to write all the different possibilities of these 3 bits. So let's take a look at step 3 next. So here we have step 3, which is to actually assign each subnet and each range. Now the first network we start with is the original network. So the possibility of these 3 bits are all zeros. And therefore, when we convert this entire subnet 1 from binary to decimal, we'll get 192.168.0.0/27. The second thing that we can do is convert or actually calculate our subnet number 2. Remember, we are only changing these 3 bits and creating the different possibilities that these 3 bits can generate. Based on our formula, 2 to the power n, we know that 2 to the 3 is equal 8. So therefore we have to get a total of 8 networks. And looking closely, these are the 8 possibilities. And simply by converting all of these binary into decimal, we have each our networks, which ends with .0, .32, .64, .190, .96, .128, .160, .192, and .224. Now, a little key trick is remember that our subnet mask is /27. So if you convert this subnet mask from /27 to the actual subnet mask, we'll get 255.255.255.224. The ending value of your new subnet mask is also the ending value of your last subnet. That's one key trick. Another important trick is this. Now, the long way of determining your subnet is to actually do it the binary way. But a simpler way is, let's remember the formula that we use to calculate total IPs, which is 2 to the power h actually. And we have 5 host bits, so 2 to the power 5 is equal to 32. Notice that each of these values are incremented by 32. So again, that's another trick that you can use to actually determine your incremental value for each of your subnets. So the cool thing is all of these here are the 8 network IDs or the 8 subnets. The next thing you want to do is to actually calculate the ranges. So let's calculate the ranges now. We already have the network IDs here. Let's actually get the ranges. Just for simplicity's sake, I'm going to draw this line under each of these 3 bits so that we will not get confused on when we're actually making any adjustments to any of the bits on the host portion. Well, the first usable host in a subnet is when this bit here, the first bit from the right, is 1. The broadcast is when all host bits are 1s. And the last usable is when all host bits are 1 except the one to the furthest right. So example, the last usable will be 11110. Now, this here is a hard way of actually calculating the ranges. But let's take a look at a much more simpler way of calculating the ranges. Well, what I like to do, and this here is a personal trick, is the first usable is a network ID plus 1. And this here will give us our first usable IP address. So let's actually try that out. So the network ID, which is 192.168.0.0 plus 1, is actually .1. Yeah. What about our broadcast? Well, our broadcast is the next network ID, which is 192.168.0.32 minus 1, will give us the broadcast for our previous network. So 32 minus 1 is equal to 31. And our broadcast minus 1 is our last usable, which is .30. See? Very simple. So let's work out this range for subnet number 2. Network ID plus 1, which is 32 plus 1 is equal to 33. And of course, we will work out the rest quickly. So as you can see that there is 0 overlapping of any addresses. Now what we can do is we can start to assign these addresses. So this first subnet 1 can be for HQ, local area network. Subnet 2 could be for branch A, local area network. Subnet 3 for branch B, LAN. Subnet number 4 could be for branch C, LAN. Now we can assign these here to our WAN links because we have 4 remaining networks and we have 3 WAN links. But the problem is this: each of these networks has a total of 30 usable IPs. And since a WAN links only require 2 IPs, we'll be wasting 28 IPs in total. So what can we do? Well, we can simply use these here as future reservations. So future reservation, future reservation, future reservation. And we can take this last subnet and actually perform something called VLSM, which stands for Variable Length Subnet Mask. In other words, we are going to take this subnet and break it down even further. So we're going to subnet a subnet. Now, keep in mind that these here, we already reserved them for our LANs. These 3 are actually reserved for future reservation. In case we have new branches popping up, we already have these networks that we can simply allocate without having to recreate a scheme again. However, this last network, we'll be breaking this down even further. So once we subnet this last network, the entire subnet mask and everything is going to change. Now this here is part 4, which is called performing variable length subnet mask. So let's take a look at actually doing this action. So here we actually have the network, which is the last subnet that we have created, the 8th subnet, 192.168.0.224/27. And what we did is we converted the subnet mask into binary together with the IP address in binary. Now, what we need to remember is this. Well, we are going to use these for our WAN links. How many WAN links do we have? We have 3 WAN links, but each of these WAN links only require 2 IPs. So what can we do? Well, remember, where the ones exist in the subnet mask, it represents the network portion. So to put simply, we cannot touch anything on the left-hand side of this line, which represents the network portion. We can only touch or modify the stuff on the right-hand side, which is the host portion. So we need 3 WAN links or 3 networks, and we need 2 IP addresses in these 3. So what can we do? Well, we can actually do a couple of things. If we borrow 1 host bit, right? So let's say we borrow this 1 host bit here. Well, we'll have 2 to the power 1, which is equal 2. But we require 3 WAN links. So let's borrow another one. So we borrow 2. Simply by borrowing 2, we end up with 2 2's 4. So okay, we have 4 networks, but how many host bits do we remain with? We actually remain with these 3 here. These 3 across here. Now, if we do 2 to the power 3, we'll get 8 total IPs. And for usable, we'll have 2 to the power 3 minus 2 is equal 6. So therefore, our WAN links only require 2 IPs. And if we use 2 from the 6, we'll be wasting 4 IPs. Well, what if we actually borrow more network bits than we actually want? What will happen? So let's take a look at this. So let's say we borrow these 3 network bits here. Well, this means we have 2 to the power 3 is equal to 2 to the 4, 4 to the 8 new networks that we will create, and we'll be remaining with these last 2 host bits. So 2 to the power 2 is equal 4. So we'll have a total of 4 IPs, which means that if we subtract 2, which is the network ID, and the broadcast, we'll end up with 2 to the power 2 minus 2 is equal 2. So we'll get an exact fit. Now you're probably wondering, but isn't that exact fit might be bad? Well, our WAN links are point-to-point links, which means that there is no growth on those WAN links. So then therefore, this calculation makes it perfect for us to determine how are we actually going to subnet this. So what we'll be doing is converting these 3 bits here in the subnet mask will be network bits. So therefore we'll get a new subnet mask and we'll be able to create 8 new networks, and each of these 8 new networks will have a total of 2 usable IPs. And these 8 networks will strictly be used for WAN links for our existing network and future networks. So let's actually make this adjustment. So what I'm going to do is simply copy the entire subnet mask here, paste it, and just going to change these 3 bits to 1s. So now we have an entirely new subnet mask for this network. And if we convert it, we'll get 255.255.255.252, which is equal to BS/30. And to fill out our calculation, it was 2 to the power of 3, which is equal to be 8 new networks from this original 192.168.0.224 network. Since we borrowed 3 network bits, we will have only 2 host bits remaining as shown here. So therefore 2 to the power 2 is equal 4 total IPs. This is inclusive of the network ID and the broadcast IP. However, it's important that we calculate usable IPs, which is 2 to the power 2, and then of course we need to minus the network ID and the broadcast IP. So minus 2, the result will be 2. So excellent, our formula is perfect. Now let us continue to the next step to actually calculate our networks and our ranges. So here, if you notice that we have actually documented all the possible bit combinations. So it is these 3 network bits that we are modifying. And of course, we have our new network IDs. And if you recall from this formula, total IPs, we have 4. And 4 is our incremental value between each of these subnets. And then we have 8, which is our 8 total possibilities. So what we can do next is simply calculate our ranges. So let's do that now. Well, if you remember, the shortcut is the network ID plus 1 is our first usable IP, which is .225. The broadcast is the next network ID, which is 228 minus 1 will give you the broadcast for your previous network, which is .227. The broadcast minus 1 is last usable, which is .226. And take a look at this. Remember, we only have 2 usable IPs. These are the 2 usable IPs for this network ID. So here we have the network ID. These here are the range. And this one is the actual broadcast. So we have 224, 225, 226, 227, 228, and you can guess 229, 230, 231, 232, and so on. And as you can see, we have 0 overlapping. So each of these new networks, which is subnet 9, 10, 11, 12, 13, 14, 15, 16, these will be used for strictly WAN links. So we could designate this link to be for WAN 1, WAN 2, WAN 3, and these here that are remaining, these extra 5, can be used for future reservation. So as you can see, we took one single network, break it down, we created 8 networks. From that 8 network, we assigned 4 LANs. We reserve a couple of networks for for future reservation, we took the last network, subnetted even further, which is called VLSM, and actually create one point-to-point links. And the cool thing is there's zero overlapping with any of these networks. So, having completed this video, you have understood the need for logical addressing on a regular network. You are able to identify IPv4 address classes and subnet mask, and most importantly, you have seen how to perform subnetting and VLSM on an IPv4 network. In the next video, you will learn how to compare, or you will learn about comparing IPv6 address types. I hope this video has been informative for you, and I hope to see you at the next one.